this then. Okay. So this is in the packet of the power rule.
Yeah.
Those questions.
These are from homework 5.
Oh, from homework 5. Those questions. Okay.
Yeah. I didn't have any question with the power rule ones. Those ones were pretty
Okay.
But
the differentiability, continuity video also was fine.
Yep.
Okay. The main takeaway from that one, we'll talk more about that later in the year, but I just wanted to intro the idea. But just to know that differentiability means that we have to have a continuous function. And if something's differentiable, then it's continuous. So that was the main takeaway I wanted you guys to get from that one. Okay. From the textbook, you have questions. Let's do 5 minutes on that, but we have to get stuff done today.
Okay, I guess we could literally just do 23, and then that'll make sense.
Okay, what page?
Should be about
111.
Okay, 111, page number 23. Oh, yeah. Because these were those limits that I had you guys do, and then you didn't know how to do them because they were derivatives. Okay, so looking at that figure on page 110, because that's what those questions are talking about. The derivative, what is the derivative?
Rate of change.
Rate of change. Another word. Come on in. What are other words we use to describe
Slope.
derivative? Slope. What are the other words we use to say what the derivative is? Yeah, instantaneous rate of change at a point. Okay. Looking at this, we can use slope to figure out what the rate of change at that point is. So 23 is x is approaching 3.
So -1.
What's the slope there?
-1.
Not -1.
Oh, is it approaching?
Oh, that's so my bad. I was looking at -3. You're right. You're right.
Yeah.
-1 at 3. I was looking at -3.
Oh, yeah.
That's 100% my bad. So yes, -1. So the slope at 3 is -1. So the limit as x approaches 3 of f prime of x is going to be -1.
Oh,
Because that's the slope there.
so then 24 would be as it approaches -1 from the right. It'd be -1 again, right? Because it's
-1.
Yep. And then
You looked at
20.
from the right.
Yep.
Okay, what's the rate of change of this line?
Oh wait, we're at -1. Oh my bad. I was looking at that. It would be 0.
Yeah, 0. There's no change there. It's horizontal.
5 and 1 from the left. Be it's like 1. Yeah, it's 1 over 1 again. So it's just 1.
Yeah, these are pretty easy to spot. We're just looking at the slope. We can't forget, all those intro ideas that we did with derivatives. Now that we can just do power rule, that's all fun and dandy, but that's just about the formulas. Everything else is still true about derivatives that we spent 5 weeks on, about its slope and about inflection points. We can't forget those things, and we're going to even use some of those today to reason through how to solve some application problems, basically.
All right, that was my only questions.
Okay.
Unless Jonah has more questions.
Don't you get one?
So you're looking at -3 there,
I
at
think
26.
from both sides.
What's the slope around that point at -3?
It's going up 1 over 1, up 1 over 1, up 1 over 1.
Then -3.
Oh, you're looking at the wrong graph. It's the graph on.
That'll do it.
Got it.
That'll do it.
Cool.
Okay, great. So, we're moving forward. We're pressing forward. We need to get through a couple of things before next week. We're moving on to our next topic. Okay, application. So now that we have the power rule under our belt, we can easily apply things. It's super easy for us to calculate derivative formulas quickly and easily now. So let's apply the derivative to some real life scenarios or just other like useful ideas that we can talk about derivatives with, which there are many. There are many real life applications which we're not going to have a lot of time to spend on today, but we will do that like almost every day for the rest of the year. Okay, example 1. Here you go, lots of words. Not really, this isn't too bad. Let f of x equal x squared minus x, and I equal the interval 0 to 2. Where exactly on I does f take maximum and minimum values? What are those values? Go ahead and start thinking through that.
Where exactly on I? So you're looking for when the rate of change is equal to 0?
Okay, tell me more. Why did you say that?
Sure, when the derivative is equal to 0. Because those are maximum.
Derivative is the rate of change. Why do you have that idea?
Because say where does it take max and min values?
Okay. Okay. So it's possible that there'd be a local minimum or a local maximum in that interval from 0 to 2. Maybe those are both in there.
Yeah.
What does x squared minus x look like?
It'd be like up and to the right. Well, actually, with it'd be a parabola because as you get closer to 0. Oh wait, no.
Why a parabola?
Well, so it's gonna be negative for like no, it's not. It's never gonna go negative. Because even like 1 squared minus 1 is 0. But yeah, it's gonna be one of these concave up. Parabola.
Yeah, it'll live above the x-axis. We could graph it. Where's your calculator? Just make the window from 0 to 2 because that's all we care about.
I think it might have fell out in the back of my car. It's not. Hopefully it's there. You can keep your weapon. Oh, you made your own. Oh, is it? Why does it look like it's like really shifted over?
What do you think?
What is shifted over?
Why is it? Wait, why is there a negative value?
It does.
Yeah, let me think about this. Oh, when you multiply decimals smaller than 1 together, it makes a smaller number. It doesn't make a bigger number. It's like 1.1 times 0.1 is
right?
0.01.
That is tricky.
So it's technically gonna live above the x-axis for everything except
For
0 to 1.
Yep. Okay.
And then the minimum would.
So we want to know where exactly on I, which is the interval of 0 to 2, does f have those maximum and minimum values? I mean, we can kind of say, okay, it's somewhere,
5, yeah.
somewhere right here. Where's the maximum value?
1.5 minus 0.25. So it would be, you'd want the biggest. .9 times 0.8 is 0.81.
Yeah, you're thinking too hard. We can do this way easier. Let's talk about the maximum and minimum values. The minimum's obviously around here. But how do we know? The maximum looks like this. If this is only my options of this interval 0 to 2, that's my highest point. Okay. So how can we think about this? Like, the graph isn't going to help us find the exact value, but doing algebra will. How could we find the minimum value? You had a good idea before that you mentioned.
Like testing?
I didn't hear you say that, but you had said something about the derivative
Equaling 0. Could you
look again here. In this interval, where is the minimum point? Somewhere in here. It's going from decreasing to increasing. So that minimum point should land
right in the middle?
right in the middle of when it changes.
So it should just be 0.5.
So if I take the slope of here, well, maybe it's 0.5. If I take the slope, I'm like negative slope. At some point it'll hit 0 and go positive. Right? So the derivative will be 0 at some point. And if the derivative is 0 at some point, well, what's the derivative? What is
Rate of change.
Yeah, the rate of change there is 0. Would that be where our minimum is at, is when the derivative is at 0?
Yep.
Okay. So now that we've established that, we have somewhere to go. Can we use that? Or I don't have any information about the derivative given to me.
Oh wait, we can find the derivative of the
Sure.
equation. So that'd be x minus 1. No,
Right.
2x minus 1.
Okay. So the derivative is, the formula is 2x minus 1.
So when
Okay.
would that equal 0?
So
Oh, it's
that
0.5.
equals 0.
That is 0.5,
Yeah, it will be 0.5, because we want when the derivative is 0, so we'll just put 0 there
yeah. Oh.
of the function, right? We want to know where's that derivative at 0. All right, now we just solve.
Yeah.
So plus 1 divided by 2, then x will be a half. When the derivative is 0, x is a half. So x is 1/2. Okay. So let's take that 1/2 and plug it into our original function to find what the y value will be. Then we'll know the exact point, because we want to know what these values are.
To be 1/4 minus 1/2. So it'd be negative 1/4. Negative 0.25.
Okay, so we found the minimum value is at the point negative 1/4.
And then for the maximum, you can just kind of use logic. You know it's going to go up and the right to infinity. So it has to be whichever one is furthest to the right. So you know it'd just be 2 is your x value, so then you can just plug in your y value.
Yes, so we can just plug in 2 because it's obvious to see that that's the highest one. If we didn't have a graph, like you're on the AP exam and you can't graph this function because you aren't allowed to use your calculator on that question, then you could be like, well, I know it's a parabola,
Yeah.
so I know that all of these values in between 0 and 2 are going to be less than those endpoints. 0 or 2 are going to be the highest ones. So then you just test 0 and test 2, and whichever one's bigger, that's your max. So if we plugged in 0, we get 0 squared minus 0 is 0. And if we plug in 2, we would get 2 squared minus 2 is 2. Okay, well then, there you go. The max is at 2.
Yeah.
Which we saw with the graph. But if you don't have the graph, then that's harder to figure out. You have to think through, oh, I have a parabola, so I know, okay. So then at x is 2, y is 2. There you go. So when we have a function, now we're able to talk about really interesting things that you weren't able to do with algebra, because you weren't able to talk about the minimum value or the maximum value of things in algebra. Because how are you supposed to find that? You have no idea. But now we can like optimize things. We're like, okay, here's this function represents finances at this company. When did we hit rock bottom?
Yeah.
Well, I'll just take the derivative. Easy. Oh, when did we have the most number of sales? Oh, at the maximum value. Just use the derivative. So we can actually talk about really important things using graphs like this and using functions that we weren't able to do with algebra. Because it's harder, it's way harder to find like a minimum value in algebra. You'd have to like test 100 points and be like, oh, I think it's about here, I don't know. Like,
you'd have to find the limit, kind of.
You'd have to find a limit, kind of. But do it by hand with a table.
Yeah.
Okay. All right, let's take it a little bit further. This is a perennial classic in calculus. It means that this problem is in every calculus course you've ever taken. So we have to do it for the sake of tradition. So a gardener wants to enclose 3,000 square meters of land using as little fencing as possible. This is valid. You might want to enclose an area with as little fencing as possible. Maybe not a garden, but the garden is to be rectangular. One side unfenced to save dollars lies along a river. How much fencing do we need?
1/4 less than what we needed in the first place.
No, because it's a rectangle.
True, but we only have.
Oh, sorry. I was thinking sorry.
Yeah, we'll be a rectangle. Let's draw a picture. I mean, let's just draw a picture of it. That helps. One side isn't going to have fencing on it because it's next to a river. We're going to assume the river is straight. It's a good assumption.
little. So if you to be as little as possible, you don't want to be. You don't want it to be as deep. Wait. Oh. No.
Let's build what we know.
Mm.
Let's build a picture. We'll start there. You draw a picture. I have to leave this here in case you're copying it down. Right.
Couldn't the river be against any side though?
Yeah.
Sure. That's just the way I drew my picture. Yeah. I mean,
Does
it
it
could be
matter?
on the short side.
Does it matter?
We want to use as little fencing as possible. I think I'd love to just take one of my long sides of my rectangle out,
So,
rather than having two long sides and one short side. Okay. What do we not know?
What do we not know? The other three fence side lengths.
No, we don't even know the length of the river either.
Yeah.
But we don't know the length of these.
Mhm.
Now what? I mean, we could just call them variables, you know? We could just give them some names.
X times Y
Oh.
equals 3,000.
X times y equals 3,000. That seems reasonable. Okay, we're building something here. Well, I want to know how much fencing I need.
So
Could I build like a function to represent that? You know, how much fencing I need?
you didn't need 2x plus y
How do you know that?
equals f.
because you only have one side.
Because we have two x sides. We have an x here and an x here. Those will definitely be the same length because it's a rectangle. One y. Okay, let's just call like, I don't know, you can pick L for length of our fence. Two x's and a y. Okay. We're getting somewhere. All right. What's tricky? What makes it so that we can't really do much?
You don't know the sizes of either of the three sides that we have left. So we can't really plug in any sort of number for variables.
Right, good. So we don't know anything about the actual lengths yet. And we're trying to optimize this. Like we want to find out the least amount we need. So we can't just plug things in. Okay. But we have two functions here that we've written. One of them's kind of talking about the perimeter, one's kind of about the area. I mean, can these relate in any way?
The perimeter is just the derivative of the area function, or the area equation. would it be the same thing like we did with spheres, where is it kind of the same concept where like it was either one or the other is the derivative of the other? I think it was like the perimeter's the derivative of the area, and maybe the other way around.
Yeah, we did last week. Volume was the amount function, and then the surface area was the derivative.
I don't know if that's...
Yes, that's actually true. There's a relationship here between the area and the perimeter. But because you don't know those formulas, we'll leave that to rest for now. But I'll just point out like the number for x in this one and the number for x in that one are the same x. Like we're talking about the same dimension. The y's are the same. We're talking about the same value, right? So could I like do a little like system of equations thing?
Oh wait, you could do. Oh, okay. Hold up. Let me cook.
I'm letting you.
You could use substitution, because x equals 3,000 divided by y. So then you can do L equals 6,000 divided by y plus y. Then you can multiply both sides by y. Divide both sides by 3,000. So you have 3,000 equals 1 plus y squared. Hold on, guys.
You're on something. Take us home.
Okay, so we'll multiply. Let's see if okay. So then you have these cancel out. Then you have y times f equals 6,000y squared. Divided by y. So you have L divided by 6,000 equals y. It doesn't help us.
Yeah, let's try to do it in terms of x instead of y. So what did you do? You did y equals 3,000 divided by x. Let's just do x. No, hold on. You did x equals 3,000 divided by y. Let's try y equals 3,000 divided by x and substitute.
Oh.
Maybe that'll be easier.
So you can do 2x squared. You can multiply just this by 1, right?
So what, we would have 2x plus 3,000 divided by x?
No, you have 2x squared.
2x plus
Yep.
3,000 divided by x.
Or but then you can multiply 2x by x over x to make it 2x squared over x. And then you have 2x squared plus 3,000 over x equals.
Okay. Well, let's go back to Jonah's idea. area and perimeter here are one is the derivative of the other. If we can think about it that way. We can also think about it as we want to know the minimum amount of fence that we need to use.
Oh,
For sure we have 3,000. Well, that 3,000 is right here in our formula.
Oh, you can get rid of L as a variable because no matter what is going on, so like 4, for example, is if you had 4 square meters or something, you'd have 2 on one side, you'd have 2 by 2, but 2 by 2, or you could do a 3 by 1, which
4 by
is
1.
yeah, 4 by 1. But the perimeter's wait 4 8.
You're so close. You just have to get over like there's a wall that you guys have in your brain. It's holding you back. Okay.
Is the
We
perimeter?
want to minimize the amount of the length that we're fence that we're using, right? So we could just like graph this function and see where that minimum value would be, and then that would tell us how much fencing we should use for the x side.
No, it would tell us how much would be total, right? Because it's L.
Well, we
equals
have
to L.
everything in terms of x right now,
Yeah, but it's all set equal to L.
which is our length,
Oh,
right?
one
Our
side.
total length
Yeah.
of 2x and y, that's our total
Yeah.
length. L represents our total length.
Yeah.
But y is equal to 3,000 divided by x. We just substituted.
Okay.
Right?
Yeah.
So we still have a function here that represents our length.
Mhm.
We want the length of this to be as close to 0 as possible, or we just want it to be the least amount as possible. Now we're definitely obviously going to have fencing because we need to enclose 3,000 square meters. But we need to find what's the least amount I need to use. So if I graph this function that we made with the 3,000 divided by x plus 2x, we could see what the function tells us is the least amount of the length that we would need. The length is equal to this function.
So to like 3,000. So to like 1,000. Or sorry, 3,000.
Could be around that. I don't know. Let's just graph and just kind of get a pulse for what we're working with.
You
You
got
need to change your window.
It's a linear function. That's weird.
Okay. Well,
That doesn't really help me if it's linear.
right. Let's talk about it. It's true. It's linear. So we could. Okay, let's think about it like this. If this is the length of our fence, we could find like the rate of change of how much fence we need. Like,
Can we change, since that's in a linear function, can't we change that to the derivative? So that way it'd just be a,
yeah, we can find L prime. What's the rate of change of our length?
it would be,
If this is our amount function for how much we need, well, then let's find the least amount of how much we need. So the derivative will tell us that rate of change where we'll have the least or most amount of fencing that we would need.
So it'd be Oh, we find this thing again. Oh my gosh. So,
It's calculus. Think about it, we're using derivatives.
So L prime is equal to 2 minus 3,000 x to negative 2. Yeah, L prime is 2 minus 3,000 x to negative 2.
So it'd be negative 3,908 x at negative 2.
What?
Because you got a minus.
No, it's order of operations. The exponent comes before. The multiplying and exponents come before, yeah. So it's 2 minus that. So you're trying to find out when the rate of change is closest to 0. We can just graph that. So put that in the calculator. 2 minus 3,000. So you can do 2 minus 3,000 x divided by x squared. I wish my calculator and phone on my back. What's in the back of my car?
So yes, we can graph this, and then we can see like the minimum value there. Or, Michael, you don't even need your calculator. Think about the last problem. When we had to find the minimum value.
So we want,
What does that tell us about
we
the
want that
derivative?
on the right to be as close to 1,500 as possible. So what number squared equals 1,500?
What did we do to find the minimum value in the last problem?
Oh, set it equal to 0, yeah.
Why?
Because it's minimum. Yeah, that's what I'm doing in my head. I am. That's
Because
what
the
I'm doing.
derivative will be 0.
Yeah, that's what I'm doing right now. So I'm trying to figure out. So it'd
You
be.
don't need to do it on paper. Promise.
You can.
You'll need to do that algebra on paper.
You're trying to make it 2 minus 2. So you're trying to make x squared equal to 1,500, right?
You're not going to be able to do that mentally. 1,500 is not a perfect square.
Yeah.
3,000 isn't either.
Yeah.
So,
It's a square.
but what is true about the derivative at that minimum point?
It's equal to 0.
Equal to 0.
So it's 0 equals 2 minus 3,000. Yeah, that's what happened. That's what I'm doing right now.
Okay, let's just solve for x.
What's square root of 50? Yeah. Yeah, that's what I have right now.
Okay, what, we can simplify this. Think back to your algebra 2 days.
Can you make it square root of 15 times 100? Oh, it's the tree thing.
Yeah, we can do 100.
So you have 15 times 100.
15.
And then it's 10.
15 can be written as...
So 15 up there, and then you have 5 and 3. So those.
5, right? No, 3 and
No,
5.
that's, yeah.
1 and 15, 3 and 5.
So, oh, you go that way. We use you go. So you
I know you do, but it doesn't matter. You can do it.
So it's gonna be 10. It's gonna be 10 times the square root of 15. Because 15 you can't break out, but 10 is gonna be 10 times 10. So 10 can break out.
Yeah, this 100 can break out, and that becomes 10. Okay, well, we're not really done. We need to interpret. So we have x is that value, 10 square root of 15. Okay, so if this is 10 square root of 15, y equals what?
3,000 meters squared divided by that. Because x times y equals that.
Yep, sure you can do that. Or you could use this one. Either way. So 3,000 divided by 10 squared 15. I actually don't know what that is next time. I mean, it'll be 300 divided by square root 15. I know that. That might be the simplest.
300.
$77.459.
For y?
Yeah.
Meters. And then whatever the x value is. Okay,
Yeah.
there you go.
So then
But we know, right?
Yeah.
So now we can find the total.
Yeah.
But it would just be 20 square root 15 plus 300 square root 15.
Yeah.
That's how much fence you would need. Now, there's no store that's selling that to you. Like, no, you're not walking into a store and be like, I need 10 square root 15 meters of this fence. So you definitely would need a round or something like that. Also, maybe you could just accidentally enclose 3,000.1 meters squared of land, and that's okay. So, you know, this is theoretical. But this is still helpful to think through because we're finding minimum, maximum values of things. Like, we could frame this as not a garden, you know, you could frame it as construction, you could frame it as anything. I could have just recontextualized this problem to something like money or whatever. We can still talk about minimum, maximum values of the rate of change of whatever. So we can use derivatives to find the length of a fence with a river or whatever. And that's amazing. That's really cool. Okay. I left you on Monday last week saying, what if I have the derivative and I want to know where I came from? That is called an antiderivative. We have like 5 minutes. Yes, we do have 5 minutes to go as far as we can. So, the idea of an antiderivative is actually pretty simple. And it's aptly named. We're just going backwards. If I have a derivative and I want to know where I came from, just work backwards.
No.
This does not sound simple.
It's a little harder to think about
No.
because it's not just like do this, do this. But there is technically a formula. Let's do this, but it's honestly harder to use than just thinking about it. So we just have to work backwards. So let's just, I have to tell you the notation. Notation for the antiderivative. So if I have a function f, the antiderivative is denoted as capital F. It's like super simple. You just use capital letters. That goes for any letter. So if I had a G, I'll just use a capital G. If I had a of F, an A of X, then I'm just using a capital A. You just capitalize the letter. That's why I've always used lowercase letters in algebra. Now you know why. It's because when you use capital letters, you're actually talking about the antiderivative. So that is how we notate the antiderivative.
And you could have a double. You could have a double antiderivative.
Sure. Yes, you could. We don't usually do that though.
Okay, so the antiderivative
Except in application.
of.
So if find f, or find the antiderivative of f of x equals x to the third.
So what you would have done
We'll
is
just have to think backwards. Backwards power rule. So with backwards power rule, we know that we'll need to add 1 to our exponent. So we know for sure I'm going to have an x to the fourth situation.
Mm-hmm.
But I need to end up with a coefficient of 1 here. So I need to have something in the front of my x term here that when I bring the 4 down, it's going to cancel out and leave me with a 1.
1/4.
Yes, if I put 1/4 in the front, 1/4 times 4 will be 1. So if I took the derivative of this, then it's really easy to see how this will become x to the third, which is where we started. Okay? Idea is simple, but you have to think a little harder about what your coefficients are. Let's do a harder one. Find g, when g of x is the square root of x.
So it would have been x to the 1/2, x to the 3/2, and that canceled out. So that times, so it'd be 2/3, right? Right, it would be 2/3 x to the 3/2.
Right, so I know that my exponent will need to be 3/2 because I need to add 1 to it. And then to cancel essentially a coefficient of 1, I would need to have 2/3 sitting in the front of my x.
So then it would turn out to be, the final would be 2/3, and then you'd have like 2x3, right? Like little box thingy.
You could write it in either form. No, I wrote that wrong. Because I don't have a negative exponent.
Oh yeah, I was wondering why you had it in the number.
Yep, and it's not a negative exponent, so it's not going to go to the denominator.
Yeah.
But that 3 is like a denominator. Or you could just leave it in the front. Write it however you like, as long as it's true. Don't put it in a denominator like I did. That's why you always check your work.
So same thing applies for applies. Oh my gosh, I can't plug that. So like if you had a polynomial, you would just do 1 at a time.
I accidentally button.
Yes, great question. And then so if you had more than one term, you would just take the antiderivative of each term. Now I need to leave you with this idea because you're going to read this in your book tomorrow, but I want you to hear it from me first.
What?
These answers are not the only answers.
Hi, okay.
There's one part that's missing. If you could just give me a minute. These answers are not the only answers. There's a small part that could change the answers. So this is a true answer. You didn't find an incorrect answer. But what if I asked you to find the derivative of this function?
Oh!
What's the derivative of that function?
It's the same thing.
What?
X third.
Yes. What's the derivative of this function?
No, it's x third again.
What's the derivative of this function?
X third.
This is all just a constant. These are just numbers. So those are just going to wipe away because the variable is going to go to x of 0. Right?
Yeah.
So even though you found correct answers here, those are not the only possible answers. So with antiderivatives, it's possible that you could have more than one answer. So here's a theorem. If f of x is an antiderivative of f, then and c is any constant, then the antiderivative plus c is just another antiderivative answer of f. How many possible antiderivatives are there of any function?
Probably infinite.
Yeah.
What? I could be in this class. No.
You could. Shut up.
I'm suffering.
No.
today.
Sorry.
Calculus is so fun.
It actually is my only fun
This one
class.
actually looked easy.
The rest of my classes just cause severe depression.
That's.
But
I
why
feel
do
like this
I,
I would
I
have
hate it
no
when like f
pressure.
of x, but
Will
then
you
they'll be
stop
like
that
f
video
of
for me?
g.
Oh, yeah.
It's like, why don't you
Thank
just
you.
leave it? You know what I'm saying?
So tomorrow you're
This-
reading
this is
3.0.